Okay, let's start now with some actual content. I already spent a lot of time with this formal stuff. Unfortunately, it looks like I have to say a few more words. The normal procedure, how it works, I don't know how your systems, the Osiris system and the registration works, because if I log in there, I get different information because I'm an instructor, so I cannot see how it looks for you. As far as I know, it works that you register, I think, over this Osiris system, and then you should, I'm not sure if you have to explicitly register for the tutorials and the practice, or if you're automatically subscribed to this by registering for this course. That's what I would expect, because it makes sense. But there is a case that some people said they have registered, but they don't appear in the practicals, or the practicals do not appear in their schedule. Then this is a mistake. So just send an email to the people who manage the system that you registered for the course, so you should appear in the practicals and in the tutorials. Then there is this second mistake that apparently happened. It should be that you're in the same group for the practicals and the tutorials. So if you're assigned to for group 2 or for group 1, you should be in the tutorials and in the practicals in the same group. And the reason is that group 1 and 2 have their tutorials on either Wednesday or Thursday, Wednesday or Monday, and the practicals at the same time on the other day. So if you're assigned to group 1 and group 3, you have the practicals and tutorials at the same day, at the same time, which obviously doesn't make sense. So so far in the last 2 years, it always worked that they assigned you to the right group. Apparently, it happened that some people got assigned to different groups for practicals and tutorials where there is a time conflict. In that case, also just yeah, I'm not sure how many people there are. So what I would just recommend now is that you go to the group where you are in the tutorials, also for the practicals. Let's just make this decision now. So that should be the easiest. Then it should work out well. So if you're assigned in the tutorials for group 1 or group 3, then also go to the practicals for group 1 or group 3. Even if you're for the practicals assigned to another group, because you should be assigned to the same group. I can send an email to the people who manage the Osiris system, but I don't know if they will still change it or not. As I said, these groups are just to guarantee that it's more or less equally split. Already, if you choose a partner for your programming assignments who is in a different group, you already have to merge, and one of you has to go to a different group than he is assigned to. And since, as I said, the practicals and the tutorials are basically, you're just there and there is a teaching assistant there to help you. So it really doesn't matter which of the tutorials and which of the practicals you go. The only thing that matters is that the number is more or less equally split, so you have a best ratio between people who are there, teaching assistants to help you, and students who might need help. Yeah, so let's just do it this way, and I send an email to them. So that was obviously a mistake in the system. Also, let me summarize this, because it might be some confusions there. There is the Osiris system, and there is the Computer Science Department website. And both of them have information about the lecture. The reason why they have these two systems, I think, is that traditionally it has been part of Computer Science Department, that they have their own teaching and lecture student assignment system. And now they want to switch it to have this Osiris system, which is university-wide. But they haven't made the complete transition yet, which is why some of the information is on Osiris, some of the information is on the computer science side, and some of the information is on both sides. And on top of that, to the two pages, there's also the page that is maintained by me, where you find the actual content of the lecture and find the announcements and special regulations for grading and so. But you should be able to find the link to the other pages via these 3 pages. I'm not sure if all 2 pages are linked from each single page, but at least we have one stop over a page. You find the way to these 3 web pages. And so the Osiris system and the Computer Science Department website are basically just for the formal stuff, time and registration and which group you are assigned to. But once that is done, then during the lecture you basically don't have to look at it. only shortly before the exams you should verify if the times changed. I usually also announce it on the course website, but it's always better to verify that on the official system, because this is something I cannot influence. If they say we changed the time of for the exam, for example, then we have to deal with it, and then they put it only on their side and not on mine, and I usually don't really get very soon informed about this either, so it will work out. Just at the beginning, I understand it's a little confusing because there are all these different rules and different pages, so you just have to find your way around. But by the time this class is over, you will know where you could have found the information. All right, now let's finally do some actual content. I said what we're dealing with in this class or in computer graphics is usually or can roughly be specified by modeling and rendering. So this is in brackets here, it's actually more an informal description. This is not a formal definition of these two terms, so let's probably put some brackets here to make this clear. So modeling is basically the idea of creating a 3D scene or a 3D virtual world, and rendering is then the process of taking this 3D world and putting it on the 2D image or on our 2D screen, on our 2D bitmap. Good, and to do this transition from the 3D model to the 2D screen, there are basically two methods. One is projective methods and the other is ray tracing. Ray tracing will be the thing that you cover a lot in your programming assignment. Your programming assignment is basically writing a ray tracer. Projective methods are not that much covered in the exercises, but in the programming assignment, but more the exercise and the lectures, which is where you do a projection of this model. So the idea is you have of projective methods, you have a 3D model of your, you have some sort of virtual world, so you have 3 dimensions in this virtual world, and then you have a model. You're modeling objects, you're representing objects in the 3D world. So this is a very simple case where we just have one triangle, one object, which is a triangle. So we have a very simple object and only one object. So this is a very simple case. We can have like a second triangle here and also have that. And now the question is, how do we get this 3D model of our virtual world onto a 2D screen? Now, if you have a 3D world, obviously the perspective matters a lot. If, like we're also here in a 3D world, not a virtual, but a real 3D world, but if I stand here and look at you, the view is different than if I would stand over there because of the perspective, because of your position and my position, which in relation to your position changed if I walk over there. So it depends on from which view we want to have the 3D image on our 2D screen. So we have, what we have to specify is we have a position of me or the viewer who is sitting there in front of the screen, and then we have the position in relation to the virtual world, and then we say, okay, when I'm sitting here looking at the 3D world, then I see it on my screen. This is what I would see on my screen of this virtual world if this screen would be a window that allows me to look in this virtual world. So it's basically similar to I take my digital camera and take a picture of you, and then I have a 2D image of you. Only here we have a virtual 3D world that we modeled, that we described with our modeling language, and then now we want to project this, create from this abstract description a 2D representation. And because of this idea that it is basically a projection of the 3D world to a 2D screen, we have these projective methods, which are, as you see here, often used in real-time applications because they're very fast, because they are hardware supported, and there are a lot of graphic APIs, libraries that support this kind of thing, which is also, as I said, something that we will not cover here. But we will cover the basics, the mathematic basics of projecting methods in the course here. So we will not learn how to program OpenGL, but when you later, after the course, get a book on OpenGL and try to learn programming, then you know how the functions that you're using, or you should know how most of the functions that you're using are actually implemented and working. And hopefully that makes learning then a little easier. All right, so the idea is, for example, you have a 3D triangle that you want to project, and now the idea is obviously a 3D triangle. You have an abstract description, which can be, for example, a specification of the vertices, because if you have 3 vertices, then you can define a triangle in a unique way by specifying the vertices. You also need to have some information about, for example, the color. If you have a more complex model, you also have light that influences how this color looks like. And then you can project the vertices. You have your position here, you have the triangle, and you can project the vertices to the position on the screen, or this area is also sometimes called viewing window, because it is like a step in between the actual screen. So what we're first doing is we take the 3D representation, project it on a 2D screen or 2D representation of this 3D scene, and then we put the 2D representation on the actual computer screen, where we have to make the transition of this abstract 2D representation in the viewing window to the actual pixels we have on the screen. And there is this intermediate step because obviously, for example, we have different screens with different resolution. So this the step to the screen pixel, the actual pixel values, is the one that's also called a windowing transformation, which is one of the exercises in the first tutorial, and also it's related to the programming assignment. Is basically this transfer of this abstract 2D representation to the actual values on the screen. Good. Yeah. So what you do is you project the vertices, and then you can draw the triangle. If like in this model you have a simple model with just a color, then you just put color in the inside of the triangle, then you're done. If you have a more complex model which also involves light, you have to calculate how the position of the light source influences the color here on a triangle. If you have more triangles, you have to calculate shadows, or if you have more objects you have in light, you have to calculate shadows that also influence the appearance. And for example, if you have a second triangle here, obviously you have to consider this when you project this. So the question is, what do you do when you have a projection where 2 or more triangles are projected to the same pixel? Like for example here, this triangle overlaps a little with this one here. You cannot see it because fortunately I cannot change the color here on this. So if we would project it, we would have it here. So the question is, how do we draw this? What do we have to consider? What do we do when 2 pixels project to the same, two parts of a triangle, a part of 2 triangles projects to the same pixel. What do we do? Question. Yeah. Yeah, exactly. Exactly. So when we look at it from our viewer's perspective, we only see the one in the front. So we have to make a decision. We have to make a first test which object is in the front, and then we have to draw this first. Or what we could also do, and what we will do in practice, is we specify the order of the object with respect to the viewer, and then we draw from the back. So we draw the one that is in the back first, then we draw the one in front of it, and then we draw the one in the very front, and that way we can guarantee that on the final image in the final screen we see the one that is closest to us and not the other ones because they were overdrawn by the drawing considered in the drawing order. Good. Yeah, this would actually be one of the lectures where we do this discuss different approaches on how to draw them in the right order and how to specify this order, because obviously the order changes with the viewing perspective. Good. So these are projective methods now, and they will actually be covered in most of the first part of the course. Ray tracing will only be covered later in at more towards the end of the lecture, but since you have to do it in the programming assignment, I will drop a few words on it to just give you a basic idea. And also the mathematics that we discussed in the following lectures are of course related to ray tracing as well, so you shouldn't have much of a problem in doing the practical assignment. In fact, the reason why I decided to keep the practical assignment is that I think they are very well. They're not only a ray tracer implementation, but they also teach you a lot about the basic stuff we do in graphics, also in projective methods. Good. Yeah. So the advantage of these projective methods, as I already said, is that it can be drawn very fast, which is why it's often used in computer animation, movies, games, and so on. But the result is not always very realistic, and that's because to get a realistic result, a realistic image, we need to do much more than just drawing objects with different colors and shadows. Because the perceptions of humans of object depends on a lot of other things. It depends, of course, on the position and the perspective that we have. It depends on the characteristic, the form, the shape of the object, but it also depends on the lighting, reflections, also other reflections. If I put another ball next to it and it reflects, that influences how I see the color of this ball here. Also, the reflection of the ball in the ball reflects back to the original ball, so it also influences. So we have a recursive situation here. Also, there are like effects that even if objects do not reflect, they putting a different object in a scene might influence on how we perceive it. So, for example, you know, all these how are they called, these optical illusions, where you have this sometimes you find it in magazines where you have like a square here in a color and a square in another color, and then they are surrounded by other objects with different color, and then you put a paper on these other objects and then you suddenly see that those original two objects that are still viewable have the same color, but if they're next to other colored objects, they look differently from the color. So what I'm trying to say here is that there are a lot of things that influence how we perceive this, and especially this recursive situation that reflections of object influence how I see them, and these reflections again influence how I see the other object. This is very difficult and very complex to calculate, and calculate in a realistic way with projective methods. Whereas ray tracing is a method which in the method itself, this recursion is considered, which is why it's easier to create more realistic images with ray tracing. So the basic idea is, instead of going from a 3D scene and say, okay, now we want to project the 3D scene on the 2D screen, we go the other way around. We say, okay, when I'm standing here, I'm looking at the screen, then I see one pixel and I want to know what color is that pixel. So the color of the pixel is, if I look through the pixel, the first object that I see with the pixel, or the background if there is no object. And then the color of this pixel representing that object is influenced by all reflections, for example, that come into this thing. So I'm following in the other direction till I come to a position where I say, okay, from now on, there can be no more ways that influence my pixel that I see here, and that way I know the color of the pixel and then I can draw it. So it's basically, the idea is, instead of with the projecting models go from the 3D model to the 2D screen, we start from our viewing position, we basically shoot a ray. That's why it's called ray tracing. So we follow a ray that goes from our eye. So this is our viewing position here. We look to that pixel, and then we go and we continue, and then we see, okay, in our scene we have here a sphere, so we know this is what we see, so we put the color here. Now let's assume we have a second object here, or we have, for example, a light source here. Then we know, because we know we can model the surface of the object. We can model how it, we know that a metal object reflects differently than a wooden object, for example. And we know, the shape. So we know how reflections behave here. So we know when we look here, then we know if there is a light. We can calculate this. That was too much. No, it was. Here we are. We can calculate the reflection vector, And that way we get to the light source, and that way we know, okay, there is this light coming here. This is a red ball, which is, for example, plastic. So we know how far, how much of this light is reflected and how the light intensity influences the color. And that way we can appropriately draw this color of the pixel here. Sorry for that. And this way you see we have to consider recursion here, because we have to influence, this influences object, also might influence this here, shadows are influencing. But this way we can do it much more easily, because we go from the position of the viewer and shoot a ray. And this is, as I said, what you will do in the programming science. So you will not do this here. These are just examples of good-looking computer graphics that were done with ray tracing. So, for example, this here, from a very distance, it really looks like like an actual image and not like a computer-created stuff. So this is not what we expect from you in the exercises. Of course, if you want to do something like this here, you're welcome. But you will start with something like this, and hopefully you will do something like this. So this is the goal for you. The very advanced students can do something like this, but this is what we expect more from you. This is more what we expect from you. Good. Yeah, so to do this, let's just start with a very simplistic model. So you can do, you know how the idea is and how it works, and can start with the exercises. In the next 2 lectures, we will cover more of the mathematical basics, so you get more information and you can really start do all the programming. I know at the beginning it's a little much, and it's also a lot of new things, so it will take a while to get into it, but usually after the first week you have no problem, and then you can really start doing this stuff. And as I said, I recommend to start in time and not wait till the deadline, because it is a lot of material, both the programming assignment as well as the content of the lecture. Good. So if you want to do this now, this I just roughly explained to you the basic idea of it. But obviously, if you want to program it, we have to have some sort of way of formally describe it. We have to have a formal description of it, a mathematical description of it. So what we need is, we need to specify our viewpoint, which is basically the origin of our coordinate system that we use. We need to specify the pixel center coordinates of the viewing window that we have, where we want to project our model, where we want to create our 2D image. We need to model the ray that we're shooting through this pixel to our object, and we need, of course, some objects, and need to know how to calculate the intersection between, or how to test if an object intersects with a ray. So in this initial very simplified version, we do not do recursion, so we only look at the first intersection point, which is a simplification. For example, you have a glass ball, and you also see behind the ball, but for now, let's just deal with the first one, and we're only looking into spheres, so we just have balls here and no other objects. Good. So the first thing, the pixel center coordinates, this is basically just a specification that we need to make. We need to say, we need to specify our viewing window, and and to do that, we basically just need to specify the corners. So if we have a lower bottom and 0, because we have a 2D, so the third coordinate is 0, but we need to know the lower button and the top right, and then we know the position of our rectangle here in the coordinate system. As you see, this is just a specification. We could also store these 2 points here, and then we have basically the same information, but the point here is that we want to know what is the minimum specification that we need to describe this in a mathematical way. We need to know the resolution of the image. That is, we need to know how many pixels are there in the width and in the height. And if we know that, then we know the number of pixels. We know their position because of a triangle. We just have to identify an order of the pixels so we can address them. So if we know pixel I and J is, like, if I is, I don't know, 10 and 20, then we need to know from where we start to count. So we need to specify, for example, that this here is 0, 0, 0, and then we know J is 20 down here and I is 10 in this direction. Good. So these are basically just specifications that we have to make, and in the exercises, both in the programming assignment and in the tutorials, you will have an exercise that allows you to that will teach you more into how to deal with this and how to do this calculation when you do a transforming, for example, from an abstract 2D representation that you calculate to the actual 2D screen and so on. Good. Then we need to describe our arrays and our vectors, our objects. And one way to do this is, the usual way to do this is using points and vectors. Both vectors and points can be are basically, from a mathematical point of view, just trituples of values. You probably know. Do you learn vector in school? Vector calculation? No? Yeah. Some of you, I think. Good. So the idea is basically if you have a three-dimensional coordinate system, then you have one value for each coordinate direction, and that way you can describe each point in the three-dimensional coordinate system exactly with these three values or this three tuple, because the order obviously is important. You have the first, the second, and the third dimension, or X, Y, and Z the direction, as it's often called. And and this is seen as a vector or as a point or a location. Now the difficult thing here is that although they are both the same in terms of how we describe them, we just need use three values to describe them. They are different from the interpretation. A vector is not a location is not a vector, but we often use vectors to describe locations. So this is often something that is very confusing, I have to admit, at the beginning, because I mean that we have the same representation but a different interpretation based on a context. So, and vectors are used to describe positions, but they are not positions. So when you hear this first, you probably say, how can something have the same representation? That is, when I write it down or write in my program, look exactly the same. And one is used to describe the other, but they are not the same, although they are described exactly the same way. This is indeed a little confusing, but the point is that it depends on the context and it depends on what you can do with it. A position is an absolute location in a 3D space, in your 3D coordinate system. So you have an absolute position, like the origin is always at this position and it cannot change. And you cannot say, I add a position to another position. So you cannot, on a map, for example, you have Utrecht, you have Amsterdam, add a position, but you cannot say, I take Utrecht plus Amsterdam is another position. You can say I go to the middle of two positions, but this is a relative position then relative to these absolute positions. And this is exactly what vectors are describing. Vectors are more a direction or a relative position. So a position, for example, if you take a position in relation to the origin, if you take a vector to describe a position in relation to the origin, then you have a location. So this is then the absolute position that you describe with this vector. But for example, when you are at this location, you can use the same vector to describe to go to another position. So the idea is, what I'm trying basically here is, so here you have a position. This is an absolute position with respect to the origin. It's an absolute position here in your 2D coordinate system. So we have two coordinates here, X and Y. And then we have, instead of three tuples, we have a pair. So we have x1 and y1 here to describe this point P1. And this is now a position, but it's also a vector because it is a direction with respect to the origin. And if we put like another vector here, this would be the vector minus 2, 3. If we add this to this point P1, we get another point P2, which is, that is 1, 2, 3, 4, 5, 6, 7, 3. 7 minus 2 is 5. And, 3 plus 3 is 6. 5, 6. And you see here, this is 5. Is correct? Yeah. 6. This is exactly here a new vector that describes this location. So this is indeed a little confusing at the beginning. Like I said, we use the same notation to describe two different things, and it's basically just the context that makes it different. Because you see here, you can calculate with this vector 2, 3. If you add this vector to this other vector that describes the location, you get a new location. But if you would draw the vector minus 2, 3, or the location represented by this, you would end up here. So this is minus 2, 3 if you draw it as a vector. So this is a completely different point here. But you can, if you add this vector to here, you cannot add this position to this position. You can, for example, draw the average between, measure the average between these two positions, like the difference between the position between Amsterdam and Utrecht, but you cannot say Amsterdam plus Utrecht is another city. That just doesn't work. So this is, yeah, you just have to, it takes a while till you understand this and get the idea of it. Good, but don't worry, vectors will be covered in detail in the next lecture. Good, so now we have a vector, and we can use this vector to describe, for example, a line or array in our situation. If we have array, then array is usually a line that is bounded. So for example, if we have our viewer observation position here, then we say, okay, the array starts here and goes in this direction. So we ignore this part here. So what we basically need is an equation for a line to describe this kind of array here. And this here is a so-called parametric equation. You see here we have a special name for this type of equation, so you already see that there will be different ways to there are different ways to describe a line. A parametric equation is one way. We will see other ways next week, and we'll also see why we have different ways to describe the same thing, because they come in different representations, come in quite handy in different situations, and sometimes it's easier to understand or easier to calculate when we use a parametric equation of a line. Sometimes it's easier to understand or calculate with when we use another kind of representation, which is why we have to learn this. The parametric equation is characterized by specifying a line by a point and a vector, and this actually is a good indication on a good example showing you the difference between an equation between a location and a vector, because P is a point, so we have an absolute point here in the space, and we know the line goes through this point here. And you see it's also described by a thread tuple. So the only way that we know that this is a location and not a vector is that it is somehow absolute. We know these are the 3 points, period. We have a vector which gives us the direction of the line or the orientation of the line within this 2D space. So here we have the point, which is the absolute position, and we know it points in this direction. And by having this parameter t here, which can be any value, if we look at the whole line, if we're not restricted, we can have any value here. And by putting any value in here, we can reach any point on that line. We cannot reach any other value, any other point in our 2D space. We can only reach values here. This is why this is an appropriate way to describe a line in a unique way. Sorry, I didn't get it.
You're supposed to stop at
45, yeah. I'm almost done, sorry. Yeah. Okay, so I have to speed up. I'm running a little over time. Good. Yeah. So this is a way to describe a line. We also want to describe objects in our model. So we said we restrict ourselves first to spheres. Spheres, this is now a different way to describe a sphere. It's called an implicit representation. We will learn later why. Sphere in a 3D space, it's a ball, so we have 3 values here. We have x, y, and z, and we have a circle, which is a ball, which is represented by a radius. This is basically best understood if you look at a 2D case. You probably all know the Pythagoras, which is if you have a triangle with the right angle, and you have 2 sides here, r, x, and y, then you know that this equation holds for these 3 sides here. And if you look at this is basically the same here, because you see I already marked you choose parameter names this way. You see, if you move the radius in this direction here, keep this point here fixed and move it in that direction, you will end up having a line, and you see that this triangle, if you draw it, that you make a straight line for the x, for the y, and a horizontal line for the x, you will always end up having r, y, and x and the right angle. So this equation will always hold, which is why it's an appropriate way to, in this way, describe a circle in 2D, and it generalizes to a sphere in 3D. Good. Now this is a sphere around the center, but if we want to have it anywhere in our 3D space, we just have to subtract the center of the sphere from this presentation, representation of the sphere around the center. It basically comes down to, we take every point on the sphere and move it by a vector, in this case, which is c, to a different position, and that way we get the sphere which is at the appropriate position. So the center moves with this vector c, or is represented by the location c, and all the points on the sphere are moved there by just adding the vector or subtracting the vector c from the points we have calculated on around the origin. Good. Alright, so we have spheres, we have rays now, and what we want to do now is we want to calculate the intersection of a ray and a sphere. And I can make this quickly because this is also part of the exercises from the tutorial. So we have a representation of a sphere, we have a representation of a ray, and we want to know which points are both part of the ray, are the intersection points, and the intersection points are obviously part of the ray and also part of the sphere. So they have to fulfill both equations, and so how we calculate this is we take one equation and put it into the other one, and when you do this, then you see that you only have one parameter, which is t, and then you can solve this by to the parameter of t, and then you get the appropriate values for t. And there is, you see here, if you solve this, this is a quadratic equation. And so it comes down to this, you probably know this from school. If not, then you'll learn it now. This is, if you have a quadratic equation that looks like this, and this is what you will get when you change, when you modify this with a little basic algebraic changes. And then you know you can solve this equation by x12 is minus b plus minus square root b to the power of 2 minus 4ac divided by 2a. So you probably know this from school. If not, it's just a formula that you have to know how to solve this. And the question, so this is just some basic mathematics, but as I said, in computer science we're not in computer graphics, we always have a meaning behind these basic mathematics. So the question is now, what is the interpretation of this in from a computer science perspective? So first of all, how many solutions can we get when we calculate this? 2. Okay, I have to finish. Good. Yeah. So I will come to the practicals, and then we can discuss this there.